Okay, problem 5. We want to count several problems in this question. So first one. So we are in a pizzeria. We have a choice of 10 different ingredients or toppings. We want to choose 3 different toppings in the first question. So how many pizzas can we order with 3 different toppings? So we have 10 pizzas and we want to 10 toppings and we want to choose 3. It is 10 choose 3. Very simple. Now part 2, we are asked that what if we can have repeated toppings. For example, let's say we choose topping A and topping B, and we will say that please duplicate this topping for me. So basically the pizza will be with toppings A, B, B. So to count the number of pizzas with 2 different toppings, first we choose the toppings. So it is 10 choose 2, and then we have a choice of which topping to duplicate basically. So we should multiply this by 2 so we can duplicate B or A. So this is the total number of different pizzas that we can order if we want to use 2 toppings. And if we want to use 1 topping and simply repeat it 3 times like A, this number is basically 10 choose 1. So the total number of pizzas, so the answer for part 2 is 10 choose 3 plus 10 choose 2 times 2 plus 10 choose 1. Okay, now problem 3. We have deck of 52 cards. We want to see how many different 4-card hands we have. So this is very simple, just 52 choose 4. You need to choose 4 cards among these 52 cards. Part 4. How many 4-card hands consist only of face cards? So first let's see how many face cards do we have. We have 4 face cards in each suit. So overall we have 16 face cards, and we want to choose 4 out of these 16 cards, so it is 16 choose 4. Okay, now part 5. How many 4-card hands contain at least 1 queen? So to count the number of hands with at least 1 queen, we use a trick that we say basically this number is the number of hands without any constraint minus number of hands with no queens. So this is exactly the number of hands with at least 1 queen. So what is the total number of hands? It is again 52 choose 4. How many queens do we have? Overall we have 4 queens, 1 for each suit. So number of hands with no queens is 48, which is 52 minus 4 choose 4. So this is the answer for part 5. Part 6, I write it here. How many 4-card hands contain 2 cards of one suit and 2 of a different suit? So to count the different ways to basically choose the cards in this part, we first pick the suits. So out of 4 suits, we choose 2 of them. and then we need exactly 2 cards from one suit and 2 cards from the other suit. So a suit has 13 cards, so we choose 2 cards from the first suit, 13 choose 2, so this times, similarly times 13 choose 2 cards from the other suit. So this is the answer for part 6. Part 7, how many 4 card hands contain 4 different suits? Okay, this is very simple. We need to pick 1 card from each suit. How many cards do we have? 13 cards, so we can pick 1 card from 13 cards in 13 different ways. So this is just 13 to power 4 because it is 13 times 13 times 13 times 13 for each suit. Okay, you can also think it like 13 choose 1, 13 choose 1. Yes. Then part 8, how many 4 card hands contain a contiguous sequence? So a sequence is defined for us. Basically the values are important, not the suits, and we are told that A can be counted both as the lowest and highest card. So the sequences, different sequences, start from A 2 3 4 and goes up to J Q K A. How many sequences of this type we have? 11. But remember that the suit is not important. So for each of these cards we have 4 choices. So for example, in this sequence A can be chosen from 4 different suits, similarly for 2, 3 and 4. So the total number of hands with this property is 11, the number of sequences, times 4 to power 4. So first we pick the sequence, and then we pick the 4 different cards of the sequence in 4 to the 4 different ways. This is the answer to part 8. Okay, part 9, we want to see a number of different anagrams by the letters of the word piazza with 3 Z's. Piazza with 3 Z's. We can see it has 7 letters. So how many different ways we can order these letters? 7 factorial. But there is a point here, which is that orderings of Z's and also orderings of these 2 A's are not important, but we are counting it in the 7 factorial. So we need to divide 7 factorial by 3 factorial, the different orderings of Z's, because we have 3 Z's, and 2 factorial because we have 2 A's. So this is the number of different anagrams with the letters of word piazza. Okay, part 10, how many binary strings of length 10 do we have such that we have exactly 4 ones? So let's write down a binary string of length 10 with 4 ones, for example this one. You can see that to count the number of these strings we basically need to choose the position of the ones only. So let's say this is position 1 2 3 4 up to 10. We just need to basically choose the positions of the ones, and then the zeros will be put to the other positions automatically. So how many strings do we have? out of 10 positions, choose 4 for the ones, and this is the total number of binary strings of length 10 with 4 ones. And finally, part 11, we have n boxes of different sizes, each one big enough to contain all of the smaller boxes at once. We may nest the boxes in 2 different ways, so we can basically put the boxes side by side, and also each smaller box can be contained in any larger box. For example, let's say we have 3 boxes, 1 smaller than 2, smaller than 3. Let's see how many different ways I can nest these boxes. Box 3 certainly should contain 1 and 2. Now I can put 1 and 2 aside. So this is one way of nesting, and another way is that 1 is contained in 2. So 1, 2, 3. We can do the similar example for 4 boxes, and we get the idea how to count the exact number of nesting. So we ask the following question for box 1, that what is the smallest box that contains box 1? So box 1 can be contained in box 2, 3, up to box n. So the smallest box that contains box 1, we have n minus 1 different choices for it. So basically we can say that we can nest box 1 in n minus 1 different ways. How about box 2? Box 2 can be contained in box 3, 4, up to n. So we can see we have n minus 2 different ways of nesting box 2. And similarly, box n minus 1, we can only put box n minus 1 in box n, so we have only one way to nest box n minus 1, and of course box n should contain all of the boxes, so only one way to nest it. So we can see overall we have n minus 1 factorial different ways of nesting these boxes.